Hey, let's take a look at section 1.4 here, function notation. So we're going to get to this f of x business that we've probably already seen before. So yeah, let's get to it. So we usually think of a function as a process by which the x is matched to the y. So there's some sort of process, right, that happens that I'm going to put an x in there, and I'm going to add something or divide or maybe do a square root or something, and I'm going to get my y value that goes with my particular x value. Something that we'll see later, I think we've already seen it in the previous section, would be this, the picture, right, of my little function machine. These are real numbers here. So yeah, real number inputs and outputting, we're going to have this notation here. This is our y value that goes with our x that we started with. Okay, so wonderful. Okay, so when we talk about functions, we're going to use the variable y and the notation f of x interchangeably, right? So these two things are the same. We're going to use different words sometimes to describe x and y. Just in the textbook, it's just going to, it'll say maybe independent variable. Maybe it'll say independent variable instead of saying x, or we could use any other letter as well, right? Sometimes we'll see other letters, but yeah, the one that goes with independent variable, this would be dependent, right? What else do we use? Maybe input or output. We use different words for these things in different contexts. Maybe refer to the text for more of these. Usually, it's going to be clear. We're going to have an x, we're going to have a y, and that'll be that. Okay, so let's make a function here. So suppose function f takes a real number. We're going to call that real number x, and we're going to apply the following steps in sequence. So our function, and we're going to call it f of x. So this is number one. We want to take that number that we're getting, our input x, right, our real number, and we're going to divide that number by 2. So to write that, what would we write? X over 2, right? Because we would take our number, x, and, well, divide by 2. Okay, great. So that's our first step. So done. And then our second step, what do we do? Subtract 9. Okay, well, minus 9. We're done. So be real careful on these where we're doing these things in sequence. Maybe consider whether or not, whoops, now it's blue. Consider whether or not these things are the same, because it's going to be your temptation to do this. Now, thinking of order of operations, if we would carry out these operations, I would take my number that I inputted, so I would have my x value, and order of operations, there's grouping symbols here, right? We don't write them because they're just implied, but this is somehow grouped together, right? The numerator. So we would do that operation first. So those would be in a different order. So be careful with this, right? We want to do things in order. First, we divide by 2. So we would have our grouping symbol here is implied, right? So, all right, we did it. Super. Okay. So we can do another one. Suppose a function takes a real number, applies the following steps. So we're doing the same thing. We want to take our number, and again, we're going to call it x, right? Or we could call it t, or we could call it whatever we wanted to. We could use any letter here we wanted to as well. I think in the system it'll specify what it wants you to use, or the instructions will be clear. Okay, so we want to take our number x. So we want to start with x, and we want to add 3 to it. Oops, keep moving the screen. Don't mean to do that. So we want to add 3 to our number. So plus 3. There you go. Okay, then we want to take what we got from that step and multiply by 2. So again, be careful with this, because your temptation is just going to be to put a 2 right there and be done with it. But that's not the same as what we want, which is multiplying by the whole thing from step 1, right? We take the thing from step 1, so our number plus 3, we want to multiply that whole thing by 2. So we've got to have those parentheses in there. Now, when we simplify this, we would distribute. So we would have 2x plus 6, right? 2 times 3 is 6. So we would get this. I think that the WebAssign will accept either one of those. But anyway, be very careful that we include those grouping symbols. Just in general, using grouping symbols is going to be to your benefit. You'll make less mistakes the more, I guess, organized you are about, what comes first, what comes second, that sort of thing. Okay, great. We've got more examples here. So this is a little bit different, right? So this idea here, when we write that, we mean that we're going to put -2 for x everywhere we see it in the function f. Okay, so that's all we're going to do, right? So f of -2, we're just going to put that -2 wherever we see x. So I'm going to leave these parentheses open. That's where x would be, right? We can use a color. So we put a -2 here. All right, and now we just simplify it. We're going to carry out these operations. I usually do it like this in my work, right, with the grouping symbols here, so that I make less mistakes with the negatives. So yeah, be careful with that, kind of a bookkeeping sort of thing. All right, anyway, we can do this, right? -2, square that, we get 4. -2 times -2, negative times negative, that's positive. And then we have 4, right? And then this guy, we got -3. Okay, so this is 8 minus 3, so 5. Okay, great. And we would say, f of -2 equal 5. Wrap it up into a neat little package. There we go. Cool. And we would say, this is the function value at x equal to -2, right? Sometimes we might call this a y value, right? Later we're going to need to think of these things as ordered pairs, right? This is our x value, and this is our y value. And later on, we're going to think of these as ordered pairs, and we're going to be drawing graphs. But we're not doing that quite yet. Just, that's where we're going. Okay, let's do part B. We're just going to put a 0 there. So f of 0, we're just going to do the same thing. So everywhere I see x in that function f, I'm going to put a 0. So 0 square minus 2 times 0 minus 3. That one's pretty quick. Usually when we find f of 0, most everything cancels out, and that works out great because, this is 0, this is 0, and then we have -3. And we would say f of 0 is -3. Part C, we can do this one. Whoops. I guess we're not really doing ABC here, are we? We're doing part I, double I, 3 I's, whatever. F of 1, we want to do that one now. F of 1. Okay, so we got 1 square minus 2 times 1 minus 3. And we can do this. We get 1 squared is 1 minus 2 minus 3. Okay, and we just do this in order. We've got 1 minus 2 is -1, minus 3 would be -4. So f of 1 is -4. Okay, super. And if we really wanted to, we could start thinking about what a graph would look like, because we're going to eventually be doing this, right? So we could put these points on there, right? If this is our x value and this is our y value, we could draw those as ordered pairs, right? We would have -2, 5. This would be 0, -3. This would be 1, -4. Let me change the color on that. All right, so there, now it's orange. So these ordered pairs, we can plot them, right? So -2 goes with 5, 1, 2, 3, 4, 5. Boop. 0 goes with -3. 1 goes with -4. And we could start, drawing a picture and trying to see a pattern. Now, if I'm trying to see a pattern here, I'd probably want to pick an x value in there, right? So I would know if I needed to put a point somewhere in here, and it's likely that it's going to be between there somewhere. Anyway, we can start drawing pictures and start thinking about pictures and conceiving of these things before we do it. But yeah, we're going to see that kind of stuff later. So let's do the other examples here. And now that's gone. Okay, so part B here. Let me just write f(x). I should have done this while I had it paused, huh? Oh well. So there's our function, and we want to do part B, right? So f of 3x. So we're going to just do the same thing here, right? We're going to put 3x where, so put this wherever we see x. And f. Okay, so we're going to take our function f, and everywhere we see x, I'm going to put, whoops, I was thinking while I was writing instead of writing while I was writing. Okay, so we're going to put in here 3x now, right? Everywhere we see x in the function f. So now we can come down here. So f of 3, whoops, golly, is this, right? So we can square that along the way, right? We know that 3x squared, that's going to be, the quantity 3x squared is going to be 9x squared. And then this guy, we got -2 times 3, so -6x, and we got -3. So there we go. So even if we're not given a specific number, that's fine. We're just going to put whatever's there, we're going to put that in for x. Okay, great. That one's done. Now we want to do 3f of x. Okay, this one, these can be kind of tricky because we're thinking about implied grouping symbols here. This is one object. This is one thing, right? F of x. We see this notation and we're tempted to think that it's multiplication here, but this is one object. It's a function, right? So it's defined up here to be this mess of stuff with the x's, right? So when I write 3 times the function f of x, I can just put the function f of x right here. So we just put the x squared minus 2x minus 3 in there. So that's 3 times our function f, right? That's the same thing. And then to find what we want to type in or what we want to give as our response, we would probably simplify this by multiplying that 3 through to everything. We do the distribution, 3 times this one, 3 times this one, 3 times this one. So we have 3x squared minus 6x minus 9. And there we go. So there we have it, part B. Yeah, great. All right, let's do the same thing here with part C. So we're still using that same function, right? F of x minus 1. This keeps moving on me. We're just going to put, just like we did before, right? We're going to put x minus 1 wherever we see x. So x minus 1 squared, right? Minus 2, x minus 1, minus 3. So everywhere I see x in my function f, right? So right there, right there. Okay, and now we just square these things, right? Or square this thing. We recall, and we're going to be doing this a lot, so when we're simplifying things or just during processes, we're going to be squaring binomials a lot. So, I mean, if we want to, we can absolutely do that whole FOIL business, right? This one times this one, this one times this one, right? We can do that. So we get x squared minus x plus 1. So we got x squared minus 2x plus 1. It's going to work out the same time, or excuse me, the same way every time we use something like this. Every single time it's going to turn out like this. So if we do ourselves a favor, we can remember this pattern and just kind of jump right there, right? We've got the first thing. Oops, I'll turn it back to green. We've got the first thing in our binomial squared plus 2 times the product of the things. So 2 times these is 2x, so minus, right? Minus 2 is negative 1 times 2. So we got, right? And then plus 1. We're just following the pattern, right? Okay. And then we have this one we can distribute. So we distribute, right? And just multiply 2 through here. Well, we could probably jump and skip the parentheses part, right? Negative 2 times x, we would have negative 2x. Negative 2 times negative 1 would be positive 2, right? And then we got negative 3. Okay, now we're just collecting like terms. So x squared minus 4x here, right? We got 2 of these guys. And then 1 plus 2 is 3, minus 3 would be 0. So there you go. So we got f of x minus 1 right there, and that's what we would write. Okay, so I guess the point is, we can put stuff other than just numbers into our functions. All right, we're still on C. So now we want to do f of x minus 3. Okay, so this is kind of like this one here, right? So we just want to write this function, and that's this thing, right? We've got some expression that involves x, right? So f of x is that, so we've got x squared minus 2x minus 3. That's just f of x, and we want to do minus 3. Okay, well, we've got the function minus 3. So really, these are the only like terms here. So we're just going to combine those. So we got x squared minus 2x, and then minus 3 minus 3, so we got minus 6. There we go. And that was easy, or relatively easy, I suppose. Now let's do this one. So we've got f of x plus f of 1. So we're kind of combining this idea here, I guess. Okay, so we've got the whole function, x squared minus 2x minus 3. All right, that's that part. And then we got plus f of 1. So now I'm going to put f here, but I'm going to put 1 in for x. So I've got 1 squared minus 2 times 1 minus 3. Okay, so this thing here is f of x, and this thing here is f of 1, right? We could go do this beforehand. We could, do this off to the side, maybe do our little f of 1 right there. If you want to, go ahead and do that. And that might be your way that you feel comfortable organizing it, and do that. But let's get on with it here. So we got x squared minus 2x minus 3. That's not changing. And then we're going to add whatever this thing is. So I got 1, right? 1 squared is 1. Minus 2, so that's negative 1. Minus 3, so we got negative 4. Okay, so now we've got x squared minus 2x, right? Those don't have any like terms, but now we've got minus 3 plus minus 4, so we got minus 7. And there we go. All right, so we would say f of x plus f of 1 is that thing. X squared minus 2x minus 7. Okay, great. So moral of the story here, we can substitute our function in and simplify the result, right? And we don't have to put necessarily just numbers in there. We can put whatever we want. Maybe so. Just very directly, I had somebody ask me. One of the homework questions said to do this: f of a. We'll just put an a in there, right? So this is a squared minus 2 times minus 2 times a minus 3, and that's it, right? We're just going to put whatever's there in for our x, and yeah, that's it. Okay, what's next? Okay, so this is kind of the same thing, right? We're just going to plop a 5 in there. So let's see what happens. So f of 5. We're going to do the same thing we did up there, right? We're going to put 5 wherever I see x in this function right? So right there, right? So simplifying this down, this is not real, right? This is our imaginary unit, right? Maybe I'll write that in a better way. This is not real. So this is well, what we should say is that we want our functions to have real number inputs and real number outputs to say that they are defined. So we have to, that was part of our definition in the textbook. I would, I guess, refer you to that. But the moral of the story here, we want it to be real, and this is not real. So what that means is 5 isn't in the domain of F, because that does not give us a real number output. It might be a good idea to think about it in this way later when we're talking about functions and their domains in more generality. But moral of the story here, we don't get a real number, and that's not good, right? We want real numbers, so this doesn't give us a real number. And we can think about back when we first learned about radicals here, right? We've got a square root, and we remembered stuff like this, right? If I had maybe square root of -2, I can't do this. There is no number whose square is negative. So these things don't exist. So if I have, something under here, this needs to be non-negative. Non-negative, right? That's a big deal. So we're going to talk about this in more detail a little bit later. So let's get to the other example real quick. Maybe I'll put it right here. So if I want g of 2, we're going to do the same thing, right? We know what we're doing. So put the 2 in for the x. So 2 plus 2 on the top. And then we got a 2 squared minus 4. Okay, so we can do this. We got 4 over, what is this, 4 minus 4. And then we see what's going to happen, right? We got 4 over 0. And we know that this is undefined, right? Think about division, right? Does it really make sense to divide something into 0 parts? We can explain why we can't divide by 0 in a couple of different ways. But we know that we can't divide by 0, right? So well, we would say the same thing, right? This doesn't give us a real number, so we'd say 2 isn't in the domain of G. And yeah, and let's say something here like we did up here. So if we have a fraction, oh yeah, that's right here. Oh boy, good. Let's say this in general. So domain of a radical function. Let's write this as kind of maybe. Let's write it in words. So the domain is the set of all x such that any radicand is non-negative. Right? So if we have something that looks like this, our domain is the set of all x such that g of x is non-negative. So I want that to be larger than or equal to 0. Right? Okay, so we can write it in words, right? And this is kind of a more mathy way we could write it is in set builder notation if we like, right? We can say the same thing about rational functions too, right? If I have something, well, for rational functions, we would say the domain is the set of all x such that no denominator is 0. Okay, maybe we don't need the exclamation point. The emphasis is already there. That's implied, right? Okay, so we could write this if we have a function that looks like this, maybe g over h. Domain here is the set of all x so that, what, our denominator is non-zero? Right? Okay, great. So we just need to find those sets, right? So let's have some examples. Maybe if we have f of x is x minus 1 under the square root. So, well, what are we going to do here? Well, it's a radical, so we need the stuff under here to be bigger than or equal to 0. So we're just trying to make that true, right? So our domain is going to be the set of all real numbers. We're going to start with that, and we're going to have the set of all real numbers such that that thing is true. So, well, take our function here. So if we're very strictly putting it into the nice little guy, we need that to be bigger than or equal to 0. So x minus 1 larger than or equal to 0. And we can solve this. These will get slightly more complicated as we go on. But for now, they're relatively easy to solve an inequality here. And we can give this in a couple of different ways. We can give it in set builder notation, or we can give it in interval notation, right? X bigger than or equal to 1. So 1 to infinity. We can write it like that if we want to. So we can say our domain is this, which is equal to this. So, we could give it in a couple different ways. We could write it in words as well. We could write, the set of all x such that x is bigger than or equal to 1. So let's do another example here with a radical. So if I have maybe f of x is, let me put that back on the green. So let's have maybe f of x is square root of 3x plus 1 minus 5. So here's my function here. So it's still a radical function here, because I've got a radical going on with a square root in it. So all I really need is this thing here to be non-negative, right? That's it. The other stuff doesn't matter. That x doesn't even affect this, so I don't even worry about that. And the 2 here, I would do this operation first, so that the 2 is irrelevant to the domain as well. So really, all we need is the radicand here to be non-negative, right? Greater than or equal to 0. So we would go and solve that, right? We can subtract 1 from both sides, and then divide by 3. Right, and we can write it in set builder notation if we like to do that, or we could write it as an interval as well, and that's it. Domain, that's our domain. Okay, super. Okay, so we didn't do any examples of something that might look like this. So with this one, recall that our domain here is going to be the set of all x such that no denominator is 0. So I cannot have 0 in that position right there, right? So we need non-zero, right? We can't have a 0 in there, right? So let's find what makes it 0. So 2x plus 1 equals 0. So let's find the x that makes that happen, and we could just get rid of it because we can use all the other real numbers, right? We want the set of all real numbers such that the denominator is non-zero. It'd be easier to write what that set is if we just eliminate what this number is, right? Instead of enumerating all of the other things in the set. Anyway, let's do it. So we can just solve this guy, right? Subtract the 1, and then we divide both sides by 2. And there we go. So we cannot have this, right? We want that to be true, right? So we can't have this, and we can write it in set builder notation, or we could write it in interval notation, right? We could write it negative infinity to negative 1/2, union 1/2 to infinity. Don't forget the negative there as well. Right, we're just plucking out this one value in our number line. Remember what this looked like? Right, we would have an open dot and it'd be shaded this way too. Right. Okay, super. Maybe we're good with just one example here, because we just need this thing to be non-zero, and we know how to solve equations, and doing stuff like this isn't too tough. I hope that solving equations in one variable is automatic. Maybe you've checked out that prerequisite assignment. I hope you did. Let me know if you have any questions or had any questions about that, by the way. Okay, so let's make some sense of what I've written here. So modeling with functions sometimes makes us want to alter the domain to reflect it. Okay, so sometimes physical constraints make it so the math stuff we write doesn't really make any sense. Let me give you an example. So let's pretend like we've got a basketball player, right? And here's our basketball player, and that basketball player is going to take a shot, and the basketball, I know that it's not the right size, but the basketball is going to go like this, and it's going to hit the hoop, and it's going to go in the hoop. So I know the path of that basketball is going to be bounce, 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 and then it's going to get shot, and then it's going to go straight down, isn't it? Well, more or less straight down is the ideal. Once it goes through the net, and it's going to direct it down there, right? Well, the math model that I would draw, or that I would create, would probably involve the highest point of the path, and I would want to model it. All of this I want, right? And if I want all of that, I need the rest of the math object that makes this happen. So that would be continuing the pattern. It would look like this, and it would go down, not in a straight line, but it would continue on, right? So my math model for what the situation isn't going to model what the real world situation is past here and past here, right? Well, so if we think about this on an ordered, coordinate plane here, I might want to make my math model such that it's this curve here, but I only consider, the set of x where 0 is less or equal to x is less than h, where h is where the hoop is, but hopefully this is clear. We would not consider this branch of it in the real world, because that's not what's going to happen. It's going to bounce off the backboard maybe and go that way, or it's going to go down the hoop, ideally, I guess. Anyway, hopefully we get that idea. Wonderful. Piecewise defined functions. So there are typically problems. People typically have problems with piecewise defined functions. Let's look at these. So piecewise defined functions. It's just like it's worded, right? It's defined in pieces. So let's just have an example. Okay, so these are going to look something like this. So we've already seen a regular old function that uses stuff that looks like this, right? These are our rules. I mean, we could use the word rules, I guess. These are functions split up into three pieces, and it's split up into three pieces by our domain regions, right? So if our input is here, we're going to use this rule, right? If our input is here, we're going to use this rule. If input is here, we're going to use this rule. So we're defining a function in pieces, right? Piecewise. So this one has 3 pieces, and we're defining the pieces by domain regions. So this one is the region, x less than -1. So we have negative infinity to -1. That's kind of ugly there. That's beautiful. This guy, we would have everything between -1 and 2, right? And then this one, we would have everything bigger than 3. Okay, so we've got real number intervals, and when we want to, let's evaluate this first. So if I evaluate this, maybe do f of -5. So I want to put this wherever I see x in the function f, but I don't know which one it is, right? Because it's pieces. I don't know which piece it is, but we do, right? We can put it in those. So we say, well, which one is this in? Which domain region is this in? We have -5. So we would just go one by one and say, well, is -5 less than 1? Yes, it is. So we're going to use this rule here, right? So we would put -1 into that piece. So we got -5 plus 1. So we've got -4, right? Great. If we do f of maybe 0, we do the same thing. We take 0. We would go over here to our domain regions. We say, which one is it in? Is 0 less than -1? No, it's not. Is 0 between these two numbers? It sure is. So we're going to use this rule here. So we got 2 times 0 minus 5. Oop, we don't need that. All right. So now 2 times 0 is 0. Minus 5 is just minus 5. Okay. So hopefully we're getting the idea here. So if I would put in maybe 3, right? So it's not in this one. It's not in this one. It is in this one, right? So I would have 3 times 3. So that's 9. Okay, cool. And going back to that, talking about the graphs, these give us ordered pairs, don't they? So we'd have -5, -4. We would have 0, -5. We would have 3, 9, 9. Okay, great. We'll get back to that here in a sec. But let's maybe think about one more. So if I wanted to do f of 2.5, so I want to do f of 2.5. So I would go and look in my domain regions. All right, where is 2.5? Is it in this one? No, it's not less than -1. It's not between these two, no. And it's not bigger than or equal to 3, so it's not in any of these, right? What we're going to say in this situation is this is undefined, right? Because it's not defined, right? Our domain regions don't include this number, so the function value just doesn't exist there, right? It's not a thing. Okay, so great. Let's think about what this would look like as a graph. Because we have ordered pairs, right? If we would start drawing a bunch of ordered pairs, we could absolutely do it like that and just see a pattern, and we could do that. But what would probably be in our better interest is to think about this just as a function in pieces, right? We'll probably talk about this later more, so maybe we can give this a fairly quick treatment. So a function, right? So for any x input, my output is right there, right? So any x I put in there is going to look like, if I had y equal 3x, if I have x values bigger than or equal to 3, my graph is going to look like the graph of this thing. If I have, let me write these in order, so maybe that would be less confusing if we went top to bottom. So if I have y equal x plus 1, y equal 2x minus 5, y equals 3x. Get rid of this for a minute. Okay, so we know what these pictures look like, right? So this one, we can think about this. Maybe with this one we can use intercepts, right? If I put a 0 in there, I'm going to have y equal 1, and I'm going to have if I have 0 here, I'm going to have x equal -1. So there's, okay, if I looked at this one, I could do, I mean, we could do intercepts on this one too. That might not be the most convenient thing for us to do. It would probably be easier for us, yeah, we could use a y-intercept, maybe go 1, 2, 3, 4, 5, right? If I put a 0 in there, we're going to have that. And probably our convenient thing is to use a 5 here. So if I put a 5 here, that'd be 10 minus 5 would give us 5. 1, 2, 3, 4, 5. Okay, that was not too rough. We can, okay, and then 3x, we can draw this picture. Right intercept 0, 0, and 1. If I put x equal 1 in there, I would have y equal 3. So we can plot points, right, and we can draw graphs. So for, we don't necessarily know that these things are lines, but we kind of know in the back of our head that when we have y to the first power, x to the first power, we kind of have that in the back of our head that these are lines, just because we've done, a number of graphs by hand, I guess. We're going to talk about lines later. It's probably true that we've already seen equations of lines before. Anyway, that's kind of not the point here. The point is that our function f, we wanted to know what it looks like. Well, everywhere in this domain region here, so from -1 to -infinity, it's going to look like this one, right? That's our piece that we just drew this picture from. So that's only going to look like that on this interval here. So it's only going to look like that here, right, where our x values are less than 1. Okay, well, it's going to do the same thing with these other pieces, right? This is going to look like this one. Whoops, that should be like this. It's only going to look like this where x's are between -1 and 2. So it's going to be a closed dot here, and maybe we don't know exactly what that y-coordinate is, but we could find it. And then it's going to go to 2, so we're going to have an open dot wherever that is. So it's only going to look like this, right? Because that's the only interval we're interested in. And then this one, only from 3 to infinity. So that's 2, 3. It's going to be like here, right? So if we want to go and draw the graph of our function, the whole thing, we're going to just put just this piece onto this graph and then just this piece onto the same graph, right? And it's going to come in pieces. Maybe I'm going to hit pause and just draw that real fast. Okay, so yeah, if we took this piece here, there it is. We took this piece here, that's in the middle. We take this piece here, that's here, right? And now it's pretty cluttered looking, right? But the ending result graph would be this graph right here that we've got the box around. Okay, so yeah, it comes in pieces, right? Each of these pieces, that's linear, right? We're going to talk about that in more detail later, but we kind of we know that they're lines, right? And we just put the individual pieces of the line together. Okay, I'm not terribly confident that drawing the graphs is going to be the focus just yet, but just to basically understand what we're doing, like inputting numbers, that's kind of what we want to focus on. Maybe I can do another example real fast just to bring us back to the ground if that kind of hurt our heads. So let's have another one. Maybe x squared minus 1 if x less than or equal to -1 and square root of x plus 2. Okay, so we can do this, right? If we have f of -3, I'm looking in this area for, darn it, I wanted to change the color. I'm looking for, in this area, for where do I put 3, right? -3. So we just go to each one, right? Is it less than or equal to -1? -3 less than or equal to 1? Yeah, that's true. So I'm going to use this rule here. So I've got that this is -3 squared minus 1. Okay, and we can carry that out, right? -3 squared, that's 9, minus 1, so we got 8. Great. Okay, and we can put in f of maybe 9. So this would be square root of 9 plus 1, or excuse me, 2, because we went up here and we said, okay, where is 9? 9 is not less or equal to 1. 9 is bigger than 0, so we would use this rule here, right? Put 9 in for x. So this is the square root of 11, and that's good. That's simplified. Okay, wonderful. So we'll probably think about the graph of these more later. This one is going to be a piece of a parabola, and this one is going to be a piece of a radical function, whatever those look like, and we'll talk about that later too. All right. Anyway, if you have any questions about this, please let me know. Otherwise, thanks for watching the video. Have a great rest of your day.